Let's pull this up. All right. So one thing I'm going to mention is the uniform distribution. Uniform distribution is so basic that you don't even like think about it as a distribution, but basically it's that every probability of each event happening is equal. So for example, if I roll a die, for example, getting a 1, 2, 3, 4, 5, 6 equal probability. So the distribution would literally look like, I'm just going to do 3-sided die. That's going to be easy for me to draw. So basically it's just literally equal. So usually sometimes I think the curriculum has something like it where it's like almost like a box, like it's just like a straight box across with lines. And basically it's like, oh, equal probability. Okay. So simple stuff, you can find the mean, standard deviation. Again, don't worry about like memorizing that or anything like that. If you really wanted to, you could probably look that up, but it gives you an idea of like, at least like, you know, how this is calculated. Negative binomial distribution. So this is kind of interesting. It's basically the negative part is kind of like, well, I'll just read what it says. Probability to get the number of times of success and failure within a group of number of events. So this is kind of like the binomial distribution, but a little bit different. So the idea there is that we keep flipping, like we keep doing a thing until we get the number of successes. How many times can we keep going? So my example here is statisticians just love coin flips and die rolls, just so you know. But you flip a coin and you say, okay, you will stop flipping your coin when you get 2 tails. Okay, so you keep flipping, flip, flip, flip. How many times do you expect to flip that coin? And so that's the idea of the negative binomial. So it's kind of related to the binomial. It's a little bit different, but the point is basically like you can keep going on technically forever, right? Like you can flip, 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 and maybe you're just super lucky you never get 2 tails. Note that it's not 2 tails in a row. It's just 2 tails, like, you know, some, right? So this has its own representation. Again, Wikipedia, great articles on Wikipedia and stuff like that about like all these really technical statistical distributions. Okay, does that make sense to people about this negative binomial? All right, cool. So let's see here, geometric distribution. So what's kind of interesting is that basically geometric distribution is not even like worth talking about because like, in my opinion, it's the same thing as a negative binomial, but basically it's just like you keep doing the thing until it stops. Or like, sorry, you only do it one time. So instead of having 2 coin flips, or sorry, 2 tails, you might say, okay, when you reach a tails, like roll a die or flip a coin and it lands on like tails, that's when you stop. You can also think of like a die, for example, if you ever, I don't know if this is actually a game, but like if you imagine like keep rolling the die until you hit like 1, or like if you play a game with 2 dice, you keep rolling it until you hit snake eyes, that would be a geometric distribution, which is really just a special case of negative binomial because essentially we're saying, oh, once you hit this one time, you're done. Okay, cool. It's all making sense so far? Okay. And I'm kind of going right through it real quick. The Poisson distribution. So Poisson distribution is a really interesting one. No, this is kind of like the continuous version of binomial. This is one that I think like is, how do I say this, is the one that you typically will actually use as a data scientist versus the binomial distribution, just because it's continuous. So I'm just going to read the definition I wrote here. The probability of having a number of occurrences / successes in a given interval, time or space. So what I mean by this is basically saying, how many times does something occur given an amount of time? So an example of this, a classic example is saying, all right, you know, I'm just going to give some random numbers. We have 10 customers come into a store every, like on average, every 30 minutes. So on an average 30-minute period, we have about 10 customers to come through, okay? How many customers will come in over the next 3 hours? That's the Poisson distribution of saying, okay, how many occurrences we have based on this probability that we've already established. So it's actually basically the binomial distribution, but it's a continuous version. And so this can be certain things like, for example, like, you know, bus wait times, how many customers go through, how many people, like an online store, you know, whether or not someone will actually purchase, or, you know, how long they'll stay on the site or something that's they leave, or, you know, things like that. So Poisson distribution, you'll see a whole lot. And again, Poisson meaning, not meaning, but like not poison. I believe it's a French guy who is this. A lot of statisticians, a lot of statistics is from France for some reason. I don't know the whole history. There's probably a history in there. I don't know. Anyway, and then last one, exponential distribution, which I just love that this like feels very like opposite of what we're talking about. This I'm actually talking about as an example of particle decay. So for example, if you increase over time, basically the likelihood of this happening increases over and over and over. So for example, with particle decay, you have a large number of particles that, you know, can basically have a little coin flips and whether or not they decay. And basically that can go on forever. So if you have, it's kind of like this own little particle is flipping its coin over and over and over again and see if it decays over time. The funny thing is that usually it's written as this negative lambda right here, as that we'd actually see in this case, lambda usually mean positive, like the decay rate, also known sometimes as beta, depending if you're like certain sciences and stuff like this. So like that's sometimes how it's described. But in this case with exponential growth for coronavirus, it's usually opposite of this. It would be a negative value. So basically that way that exponential is positive going up. Okay, cool. Yeah, so those are the different distributions. There is so much more, and there's even other things like beta distributions, which aren't even mentioned in the curriculum. But honestly, you don't necessarily have to go really deep into it. There's just a whole bunch of things you can do with statistics itself. But these are really common ones, especially exponential, Poisson. And then I would technically say uniform, but like no one ever thinks about uniform. Okay, sound pretty good? All right, any questions at all that I kind of ran through pretty quickly? All right, so I'll close these guys. Cool. So like I said, like other distribution from the appendix. So a quick knowledge check. So why know these distributions? So I kind of said this already, so just kind of seeing if you paid attention, right? Why should we know any of these distributions? What can we do with them?
Make predictions.
Make predictions, right? So like, hey, I know this system, like I see it's doing this distribution, I can continue it on analytically, right? So I'm gonna say from Stephen's kind of adding in there, that being that you can make predictions off the data. Once you're like, oh, the data shows that it has this distribution, okay, we can make predictions from that distribution. What's another way we could use the distribution? So instead of just looking at the data, it's a little subtle.
To describe like what we're seeing happen if we want to know, yeah.
No, great, perfect. So like if you know a situation, like for example, we know virus spread, before we see any data from the virus spread, we know what this distribution should look like, what we expect it to be, right? And make predictions from that. So we can actually base it not on just data itself and see like, oh, we have to look at the data and see what happens. We can actually say, hey, what's the situation? What's the, what do we expect for the system? What do we expect, what kind of distribution, and then make predictions from that too. So that's also just as important. So one's kind of like in some ways like hindsight, another one is more like knowing what we want to do. And what's really cool too is that you can do simulations based on this distribution, and you can build this distribution and do whatever you want without ever having to look at any data. So it can be really useful too. And that's why normal distributions are so important, because like so many things follow normal distributions. We can say, hey, we can assume this is normal. In fact, that's kind of like the joke almost in statistics. We're like, hey, assume this is a normal distribution, because we're like, that's probably pretty accurate. Okay, cool.